Okay, so.
Hi, Sarah.
Sarah, we miss you.
I miss you more.
Okay, so related rates is the next section's 5.6. So there's steps that you need to do to like successfully do these problems.
That's like proofs.
No, it's just like
I got it.
you don't have to say why you're doing something, you just have to make sure you clearly label everything. So, and a decent amount of the time you need a picture. So, alright, so guidelines. So identify all given quantities and quantities to be determined. Make a sketch and label the quantities. Write an equation involving the variable whose rates of change are given or to be determined. So the rates of change are going to be like your derivative values that you're given. Using the chain rule, implicitly differentiate both sides of the equation with respect to t. So pretty much everything is with respect to time. And then after completing that, substitute into the resulting equation all the known values for the variables and their rates of change, then solve for the required rate of change. So the easiest way to do these are literally just with examples, so we'll just go with that. All right, so a police cruiser approaching a right-angled intersection from the north is chasing a speed car that has turned the corner and is now moving straight east. When the cruiser is 0.6 miles north of the intersection, the car is 0.8 miles to the east. The police determine with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? So, I typically try to draw a picture first, and then I fill in values to go with it. Try not to get shocked. All right, so from the north, you have the cruiser and traveling that direction. It's a right-angled intersection, so the intersection is here. Car is traveling this direction. Car's over here at this point, and then we just connect them. The little right triangle. All right, so for the most part, we try to keep the variables like matching up with what they are, so like direction wise. So like the y-axis, the x, and then the hypotenuse we'll do a z. Okay, so then typically what I will do is I'll do x, and then I need more space than that. Come on. X, and then dx dt. And I'll do y and dy dt. And then z and dz dt. And then you'll fill in the values that we know, and then we'll have to find some of the other values. So, let's see. A police cruiser approaching the right-angled intersection from the north is chasing a speed car that has turned the corner and is now moving east. When the cruiser is 0.6 miles north of the intersection, so 0.6 is the cruiser, so that's the y value, so 0.6 miles. The car is 0.8 miles to the east, so the x value is 0.8. The police determine the radar distance between them and the car is increasing at 20 miles per hour. So when you see something like that, that's indicating your rates, which are going to be your, like, derivative values. So the distance between them and the car is increasing at 20 miles per hour, or radar distance. So that's going to be 20 miles per hour for dz dt. Cruiser is moving at 60 miles per hour at the instant of measurement, so dy dt is 60 miles per hour. Because of the direction that it's going to be negative, since it's going like down. If that makes sense. And then basically we can find z by the Pythagorean theorem. So until we need dx dt, we don't really need to do any calculus. Everything else is just solving, like simple. So x squared plus y squared, so 0.8 squared plus 0.6 squared is equal to, well, I'm going to do the square root of all that in one step, is equal to z. I have on my paper that it's 1, but I need to check and make sure that that's right, or if I like rounded, that's possible too. It's gonna be 1. Yeah. 0.64 and 0.36 equal to 1. Okay, so then z is equal to 1. Trying to remember to put units on all this stuff so that it's right.
Do you want me to bring this back?
Yeah, if you're done with it. Or can you ask her? Can you tell her I need it back, not the office?
You meant to give that to you.
Yes,
Okay.
I'm getting donuts tomorrow.
Okay. Thank you.
You can just lay it on my keys. Thank you. I was like, wait, I think she misunderstood what I was saying. Okay, so then now we get to use the calculus to solve this stuff. So we're going to use, unknown formula that we know works is the Pythagorean theorem. So x squared plus y squared equals z squared. So then we're taking the derivative implicitly, so that means like you're gonna, like for x, it's gonna be 2x dx dt, because we're taking the derivative with respect to t for everything. So we want all of these, well, they won't all always be in there, but we want them to be there if we have them. If that makes sense. Okay, so 2x dx dt plus 2y dy dt is equal to 2z dz dt. The derivative, throw them out front. So then I want to solve for dx dt. So I need to get it by itself. So I'm going to subtract this whole 2y dy dt piece over, and then I'm going to divide everything by 2x so that I'm left with just dx dt on this side. So dx dt is equal to 2z dz dt minus 2y dy dt over 2x. Take up a lot of space. So then we can put in numbers. So dx dt is equal to 2 times 1 times 20 minus 2 times 0.6 times negative 60 all over 2 times 0.8 and then in theory, assuming that I've done it correctly, that should be 70 miles per hour.
Multiplied by each other. Like the dz dt, that's 1 times 20.
2z dz dt. So 2 times the z value is 1, and then dz dt was 20.
Oh, okay.
So we're plugging in.
So those are like two.
We're plugging in all of this stuff over here.
Are those? So those are two separate things, like.
Yeah.
Okay.
So it was like when
I
we.
have that as like 0.8 miles times dx over dt. Does that make sense?
Like how you wrote it over here.
Like coefficient, yeah.
Oh, yeah. No, they're
No,
yeah.
coefficient. Okay. Well then.
Well, because I guess that's why I was all the more confused.
And I was like, what are you talking about? Yeah.
I know it wouldn't matter for like.
There you go.
One.
Draw a line between them.
Yeah.
It's hard because my stuff is so squished together on here. The next problem won't take up as much space, so it won't be that bad. The beauty of these problems is I actually got this from when I worked with that teacher at Bethel High School. He did these, and so he actually has taught AP Calc for so long. He knows what kind of related rates problems they're going to ask on the AP test. So that's pretty much what all of these are, ones that you'd see something similar to it. All right, so then the only piece that we were missing was the dx dt piece, so that's 70 miles per hour. So we can fill that in, and that would be officially your answer to that problem there. Any questions on that one? Now that you know that they're not coefficients.
Yeah. No, I'm pretty good. It's like it's like recap.
Yeah, you haven't gotten there yet.
Oh, I thought y'all had already done this kind of stuff.
Mm-mm. That's
Did
why
you
I'm.
not see what I just showed you? We're struggling on literally how to make it out.
Well,
Like that was a retake. Like she gave us a retake. That's how much we struggled.
I think the only retake I have is in algebra 2.
Oh, congratulations! You're smart.
That was because you had the talking class that decided that talking while I was talking was a good idea.
They talk more than we talk.
While I was talking, yeah.
I see.
I couldn't even get a word in.
Alright.
So I gave them a quiz the next day on the material that I didn't teach. And they failed. So I taught it
I got a C.
and gave them another one. Well, yes,
I-
but you would naturally just figure it out.
Yeah.
Some of them would not.
I got high C or down.
Apparently tomorrow there's going to be no pizza and no corn dogs.
Oh, I see.
Okay.
I'm never gonna be able to understand what I'm writing.
Yeah, I don't know why I have the space for example 1 so small, because the space for example 2 is huge and it doesn't need nearly as much space. Okay. Did you get that one?
Yes.
Okay, cool. So, a pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. The radius of the outer ripple is increasing at a constant rate of 2 feet per second. When the radius is 4 feet, find the rate at which the area of the disturbed water is changing. So basically, I'll draw a little picture down here. You have your little pond, and they drop a rock into the water,
Yeah.
and then it
goes around.
causes these ripples. Well, they're not perfect, but you get what I mean. These little ripples, and as they go out, these rates are occurring. So it's in the radius of the outer ripple is increasing at a rate of 2 feet per second. And then the radius, when it's 4 feet, we want to find what the rate is.
It's the pictures.
So, known values, or what we're trying to find is the area, which may or may not end up being relevant, dAdt, the radius, and drdt. So this is one where, like, we're not necessarily told what the area is, but we can find the area with the given information. And just because you can find it doesn't always mean it's relevant either.
Oh, the circle.
So, area of a circle, or well, hold on.
So when the
back up.
radius is 4 feet, we want to find its rate.
Well, and we're told that it's at a constant rate of 2 feet per second. So, how it says,
the rate of the area is changing.
yeah.
Got it. So then dr over dt. Okay.
Yeah. And then area, we can find with the information that we have. So area is equal to pi times r squared, so 4 squared. Or we can just call it 16 pi. And that's technically in feet as well.
That's the area.
Yeah. So then we're going to take that area formula and take the derivative of it. So A is equal to pi r squared. What would the derivative of that be?
2 pi r.
And then dr dt. And then on the other side, dAdt. That's the weird thing to get used to, is that they're all like with respect to t. So you have to literally take the derivative of everything, which is like where this is different, but not at the same time. So this is why I'm saying in reality, this value here for area ends up being irrelevant because there's no a left. Because all that's left is dAdt, which is what we're solving for. So this one we don't really have to like move stuff around at all. So 2 times pi times r is 4, and then dr dt is 2,
So this is just 16.
so 16 pi feet squared per second is dAdt. So that one happened to be the same value, but that won't always occur. So, let's see. Contemplating if we have time to do any of these other problems. What?
When Apple phones send pictures to my
That happens if somebody that doesn't have Apple sends one to me too.
Yeah, I don't know why. That's really annoying.
Depends on the resolution of the picture and if they're sending it like one at a time or multiple.
If they send multiple, it always ends up blurry. Or I don't know. Or I guess you can like send whatever cluster pictures. However,
Yeah.
because like Ariel sent me these pictures, and like half of them are blurry, and then the other ones just said fine.
Yeah, I don't know, that's weird. Sometimes I end up having to like email them from my mom's phone to me because her pictures always end up coming out blurry. Trying to see if we're gonna actually have room to do this problem on this thingy.
We've got like what, 7 minutes?
Yeah, I was just gonna try to draw the picture and then we can actually solve it tomorrow because it just takes a little bit to draw the picture. So basically, conical tank, okay, think of like a funnel, like, so it's round, but it's like a triangle. And so we have, let's see, it runs into the tank at 9 cubic feet per minute, stands point down, and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So basically, oh, I forgot to hit this. I'm gonna try to draw this over here. We have a tank that looks too much. I need to not make it. Okay. Something like that, more or less. And at the top, this value here, this radius, is 5 feet. We know that the entire height from top to bottom is 10 feet. And then we want to know when the water is 6 feet deep. So basically, when our water level is, well, a little over halfway, I guess. We want to know what's happening. So the way that is a good way to look at this is to like split this basically like down the middle kind of, and to look at it like triangles. So basically what we'll do is that we're going to compare what we have here with a triangle that's similar to it. Being something that's going to be like that, basically. Where we know that this whole thing is 10 feet top to bottom. We have an R value here, which is where the top of the water is. And then up here is the top of the tank. And then basically we'll be using, I'm going to gather you probably don't know the volume of a conical tank.
No, I used to. It's like, it's like half of my legs.
You're actually really close. 1/3 pi r squared h is the formula that we're going to use. So then as far as variables, we'll have V, dV dt, R, dr dt, and H and dH dt.
Can you read for me what those say on the smaller triangle?
Yeah, this R value is the top of the water.
Okay.
And then the other one is the top of the tank.
And what is that little thing on the side, the black letters?
10 feet.
10 feet the height, right?
Yeah.
Oh,
So we're going to use that with a little bit of other information to help solve basically what we're looking for. Because we know that when we take the derivative, we're not going to need the volume because it's going to be gone. We can just X that out. We don't even have to put anything there. The water running into the tank, which is the volume of it, is 9 cubic feet per minute. Probably should be writing this a lot smaller because it's not going to fit. We want to know what's happening when the height of the water is 6 feet. So that's the height that we're using. And right now it won't make sense if I tell you this, but we are going to be getting rid of dr and dt, or r and dr dt. But that won't make sense until I show you why with the similar triangles here tomorrow. But I don't have time to explain all that right now, so.